So I'm Tabetha Boyajian. I'm speaking on behalf of Debra Fischer. And within our group here at Yale is Jesse Sawicki, is a stats professor at Yale. Alan Davis is a grad student. Colby Jurgensen, Tyler McCracken, and Dave Sawyer are part of the instrumentation team. Joey Smith's another grad student, and then we have a couple other students working with us as well. I'd like to start out with an update on the Extreme Precision Radial Velocity 2 meeting, which we held at Yale last summer. It was a 3-day meeting. It had about 130 participants. It had a structure that included a very broad but deep plenary talks, and there were breakout meetings. There was plenty of room to collaborate, to learn new things and everything like that. It was very well structured. And all of the talks from this conference are listed on the program's webpage, as I listed on here. So if you just type Yale EPRV, then a Google search will come up. So that's really handy if you want to go and listen to any of those. But I think one of the most key things that actually came out of this was this paper that just got accepted a couple of months ago on the state of the field for extreme precision radial velocities. It is an amazing resource. Go check this paper out. You see all the amazing authors on here and the amount of things that are put in here, looking at things in so many different directions. It's really worth a look. And so moving on, I would like to give an update on how Yale's high-resolution extreme precision spectrometer, or ExSS, is doing. It is moving forward. Its commissioning is planned for summer of 2017, so next summer. I have 2 updates to give you right now. The first is the spectrograph and optical design. I do not do instrumentation at all, so I can't talk intelligently any more than just showing you this slide and telling you that I can give you updates based on a whole bunch of other slides that were given to me a couple of days ago. So if you're interested more about this, please talk to me after this. But here you go. This is what this looks like. It's a white pupil design for ExSS, and it's optimized for sampling and for the camera to be insensitive to pupil instabilities. This provides an additional level of scrambling and requires a specialized merit function during the optimization process. The second update for ExSS is that the vacuum enclosure design is shown here on the left-hand side, and the cryostat is shown there on the right-hand side. And again, disclaimer, I know nothing more than this thing over here has wheels, and that thing over there keeps things cool. Okay. All right, next update is on telluric. So they, Deborah and Christopher Lees, who's an undergrad, and Jeff Valente at Space Telescope developed an empirical telluric line fitting code. Next is the wavelength calibration project. So we have a laser frequency cone that got ordered from Menlo, and it arrives this summer for testing in the lab. And we're already starting to use the HARPS laser frequency comb observations to develop code for this wavelength calibration. And first effort gives us 5 centimeters per second precision, and we expect this can get a lot better. So, yay. All right. Next project update is that we are now developing techniques to distinguish between photospheric velocities and Keplerian velocities. So this is with NExSS PI Eric Ford, who I don't think is here. Jesse Sawicki is a stats prof at Yale, and some of our students. So what was done is a PCA, so principal component analysis, on simulated spectra that shows the importance of high resolution and high signal to noise. So basically, like a planet will give a simple signatures completely contained in one principal component, and then once you have spotches and plages, then this will bring complex signatures in many principal components. And so the big news from this analysis here that's important, I think, for the entire exoplanet community who's searching for Earth-like rocky planets is that getting centimeters per second precision is going to require a really, really big telescope in space. So you don't have any tellurics and you have lots and lots of glass, you get an enormous signal to noise. I showed in this plot here. You need to get up in this region over here. So this is like, talking about signal to noise around 1,000 and resolution of around 300K at least, so you can sample all of these different things. Okay. Next project I know a little bit more about is Planet Hunter. So we are working on habitable zone Kepler planets using the Planet Hunters, which is a citizen science web forum. Grad student Joey Schmidt is developing a user weighting scheme for user classifications to be based off of simulated transits in these light curves. And he's now working on the long period planet occurrence rates for the entire set of M dwarf stars. The K dwarf stars are now being shown, and that's next, but the N dwarfs have all been classified. Another item is the round 2 review. So this is after light curve and Planet Hunters gets shown and classified by at least 10 of our users. Then if it reaches a certain threshold of, they marked a certain position in the light curve as being a particular region of interest, like there's a transit there, then this light curve will go on to a round 2 and have more experienced reviewers say, look at this little clip and say yes, no, maybe. And so it's just kind of an additional filter for our classification scheme. Another part of this is that Joey is going through the known KOIs that have short period planets, and he is taking out these transits rather than masking the data and then rerunning them through the Kepler pipeline to see if there's any long period planets that are missed. And lo and behold, there's actually one that's actually come up out of this, and so they're working on doing this a little bit more. So that's pretty cool. There's more planets in Kepler data. Who knew? Okay, so for a look into the future, we are talking with Steve Reinhardt with how to show test data in the Kepler or in the Planet Hunters interface, just as we show the Kepler data there. And also, I'd like to advertise the fact that we would like to get you to think about being a guest scientist for if you're a PI for K2 data. So this just means whatever K2 program that you have and you want to filter it through Planet Hunters, so have, do crowdsourcing to, get your results in one way or another, come talk to me and we can facilitate that happening. Lastly, it's this WTF star, which I like calling it that more than the other name that people give it, just because I think that's a little weird. But things have, a lot of things been happening around this. I gave a TED talk on it that came out a couple months ago. If you haven't seen it, you should check it out. Let me see, I've been working with Jason Wright, Casey Leese, and other people here. Right now, there is multi-band photometric monitoring with the LCOGT, and also dozens and dozens of amateur observers from the AAVSO have also contributed to this light curve. There is spectral and radial velocity monitoring going on with the APF. There is infrared monitoring going on with Spitzer, and soon we'll have Green Bank observations as well as AMA. And lastly, I'd like to end with this object was found by crowdsourcing. So it was found by Planet Hunters, people looking at light curves from the Kepler mission, saw this like enormous signal that would have been missed if it weren't for somebody looking for it, or somebody looking at it with their eyes, because we weren't looking for something like this. So it was found by people looking at this data, and now we're kind of like continuing on this theme and having, giving the community a chance to be a part of this. And we're going to crowdfunding, and we're doing a Kickstarter that's happening right now. So if you please spread the word, I'd be much appreciative. I think that's it. Yes, that's it. Thank you.
About the WTF star.
Is enthusiasm for Planet Hunters continuing? Are the citizen scientists
still? The question was, has enthusiasm for Planet Hunters continuing? We've definitely had a spike in user classification since about October of last year, a huge spike. And so it's definitely like making it a lot easier to have data be pushed through that. But we do have a lot of results that are coming out of the project, and not enough people that are able to deal with these results. And so, I mean, if you're interested in, even just logging on and trying to answer questions or, yeah, anything like that, just let us know.
So what I'm just going to play straight man is that I think this is a fabulous use of the Kepler data set in a way that was unintended when it was launched. Do you have other objects or other light curves, anything like KIC 846
Well, we're able to do, once we found this, we're able to do a backward search through the Kepler data set, try and find stars that were similar, so we could try and pinpoint how unique it was. We were able to look down to a certain level of something that dips below 10% or below 5%. I think 5% was the level that we were able to check down to. With no periodicity constraints, nothing like that. And we didn't identify any, but if you go any lower than that, then it's extremely hard, because then you just get returned like all 150,000 stars. So as of now, it's still unique.
And your best idea of what's going on?
Yeah, I mean, we're still working on that. We need more data, and so that's kind of what this crowdfunding campaign is to get more data so we can look at it continuously for the next however long you want to make it. Yep.
You made me think of another question. Is this on? I'm not sure
You can use this one.
So there we go. Could you go back to the slide that says something about M-dwarf planet occurrence rates?
Yes.
Long period planet occurrence rate. Yeah. So what do you mean by long period? And this is coming out of the Planet Hunter stuff. So are you talking about like single transits or?
Yeah, single, double, triple transits. Like the parameter space that Planet Hunters is really, it's really good at identifying planets, or like the really, really long ones, because it doesn't need repeated transits like any sort of automated pipeline needs to identify a source as a possible candidate. And so clearly, like if you only have one or two transits, that's not anywhere near a confirmation. But there are a number of triples and even like four occurring transits in the 4 years of Kepler data, planets that we've found so far that have been missed by the pipelines. And this work is just based on just the M dwarfs in that sample, and looking for those kind of period ranges. Yeah.
And then just about the WTF star. Did I hear recently that there was an update about the long-term dimming of the star?
Oh, yes, yep, you probably did hear something about that. I myself have tried to stay away from it. I'm not an expert in it at all, and I definitely don't claim to be. What Natalie is talking about is that this star was observed by the Harvard plate stacks that go back to about 1890, and these observations showed in one analysis that the star was 20% brighter 100 years ago than it is now, which is really weird. Another paper came out. There were actually 4 versions of the paper. That I mean, they're revising themselves for the better, I think, every time. But it came out saying you can't use this data set to do this or to reach these sort of conclusions because of the stability of the plates and that sort of thing. I don't think it's a closed book at all. Like I think it's still open. And I do prefer to stay out of it because it's really like it's not my thing. I don't know anything about photographic plates at all. But it is a really interesting kind of like idea that, to see something like that is kind of just like, wow, like stars really shouldn't do that. And so it would be, amazing result to see that, and that it would be unique for this star as well.
Any other questions? All right, let's thank Tabby again. Okay, our next speaker is Leslie Rogers, and she is speaking on behalf of Eric Ford's team, and she has a movie that hopefully will actually play. So. All right, so.
Okay, thanks. Okay, it's a pleasure to be here to give a progress report on Eric Ford's team, which is investigating the bulk properties of small transiting planets and implications for their formation. So the main goals of this effort is to use transit timing variations from Kepler multiplanets to characterize the mass, radius, and orbital eccentricity distributions of small exoplanets. And eventually, we would like to tie the mass, radius, eccentricity distribution to insights into the bulk compositions of exoplanets, as well as the diversity of their orbital architectures. So here's just a slide showing the proposal team. So this proposal encompasses expertise, both in modeling exoplanet orbital dynamics, interpreting Kepler light curves to measure transit times, statistics of planet populations, as well as modeling planet formation and interior structure. And I would just like to highlight two of the collaborators who, though not directly funded by this project, have made substantial contributions that I'll highlight in the later slides. And that's Megan Chabran, who's a recent PhD from Penn State, and she's now a postdoc at NASA Ames. And then also Angie Wolfgang, who's an NSF postdoctoral fellow at Penn State. Okay, so just so that we're all on the same page, let me review transit timing variations. So whereas in the Doppler radial velocity method, one looks at the influence of a planet on its host star to get a measure of the planet's mass, transit timing variations rely on detecting the gravitational influence of a planet on other planets in the system. So if you have two dynamically gravitationally interacting planets exchanging energy and angular momentum, occasionally they'll appear in transit a little early, sometimes a little late. And by measuring that transit timing variations signal, you can constrain the mass and eccentricity of the system. So for many configurations of planets near mean-motion resonances, you get anti-correlated transit timing variations between the two interacting planets. And in those cases, from the transit timing variation amplitude, you get degenerate constraints on the mass and eccentricity. In more information-rich systems, with careful analysis, you can break those degeneracies and get measures of each planet's mass. Okay, so ultimately, we want to get measures of the masses and radii of these planets. So here's just a video showing the exoplanet mass radius measurements detected to date and highlighting what I think is an incredibly impressive measurement of the mass of a Mars-size exoplanet. So this just highlights the amazing sensitivity when you have the requisite architectures or planets near mean-motion resonances to apply transit timing variations that can be very sensitive to low-mass planets and out to longer orbital periods than current radial velocity instruments. So Eric Ford's team has published and submitted a number of results already, including a revised catalog of measured transit times from the Kepler dataset, and also new mass measurements for 30 small exoplanets. Further, Eric, Angie, and I have developed a probabilistic mass-radius relationship for small exoplanets. So instead of relating radius to mass as a one-to-one mapping, each radius corresponds to a distribution of masses. And with hierarchical modeling, we've definitively shown that there exists diversity in the planet mass radius measurements. Not all of the scatter in the mass radius points collected to date can be attributed to their large uncertainties, their large error bars. There's some intrinsic dispersion in the masses of a planet of a given size, as we'd expect due to compositional diversity. So other progress. So Daniel Jontov Hunter has measured the transit timing variation amplitudes and phases for all planet pairs in the Kepler catalog within 6% in terms of their period ratios of mean motion resonances. And so this is an important point actually, because it's something that sets this project apart from other bulk analyses of Kepler transit timing variations. Is here Daniel's not just looking at the cases where you can see transit time variations in the transit times, transit to transit, the high signal to noise cases. He's considering every single planet pair with period ratios within that tolerance of mean motion resonances, both to measure the transit times where they're detected, but also to set upper limits where they're not. And that's important for getting an unbiased measure of the mass radius distribution of planets. So Angie has developed a hierarchical model for the mass radius incident flux distribution of planets, whereas Megan Shabram has developed a hierarchical model for the mass radius eccentricity distribution. And we're continuing to apply and generalize these models. Okay. Now, the next few slides towards the end of this talk are here mostly to stimulate discussion and thought throughout this meeting. So here's what I think is a very compelling diagram showing the planets from Kepler that have mass measurements to date, with planets with masses measured from transit timing variations shown in orange, and the sample with radial velocity measured masses in green. And here you can strikingly see that these two mass measurement techniques are sensitive to planets, are probing different ranges of orbital period, and that there's systematic offsets in the densities measured for these two samples. Now, there are selection effects and biases that can contribute to the transit timing variation mass planets being systematically lower density, but you would also maybe expect them to have lower densities since they're at longer orbital periods, receiving less incident flux. They'd be more able to accrete and potentially retain a volatile envelope. So I think it's still an outstanding question: to what extent does this density discrepancy due to the difference ranges of orbital periods probed, or differences in the intrinsic populations of planets near mean motion resonances and those that aren't, or selection effects and biases? Here's another plot showing a similar thing. So this blue mass radius relationship is the fit from our paper to the radial velocity sample. And these black points are just showing the small planets with masses measured from TTVs. And if you just use a similar framework as we applied to the radial velocity sample and fit a probabilistic power law, kind of a power law mass radius relationship with some intrinsic dispersion to the TTV sample, this is what you get. And the point is here, it's not a good fit, or we shouldn't really consider that a good fit. And here, I just wanted to add this slide to show, or to highlight the fact that it's actually a non-trivial endeavor to get a mass radius distribution for planets. If we're looking in mass and radius, there are several other dimensions of planet properties, like incident flux, host star spectral type, host star properties, multiplicity of the planet system that may contribute. And there may indeed be separate populations of planets that aren't fit by a single component model. And so part of the effort of the project in the coming few years will be to further investigate more sophisticated models for the planet mass radius distribution and to try to assess what evidence is there for different dependencies on different factors or for the inclusion of different subpopulations of planets. Okay, ultimately, we want to get insights into planet bulk compositions and planet formation from masses and radii. And so some of what we might be interested in inferring is what's the typical mass scale for rocky planets. For the planets that do retain a gas envelope, is there a typical relationship between the planet heavy element interior mass and the mass of the hydrogen-helium envelope? Is there evidence for distinct planet subpopulations formed through different planet formation pathways? And indeed, how much scatter is there in exoplanet compositions? And so my contribution to the team is to try to interpret the noisy sample of planet mass radius measurements and distill insights into the underlying composition distribution of planets. So performed some sensitivity studies or trade studies to explore what we might be able to infer. So essentially this involved taking a parametrized model of the planet mass composition distribution, generating a simulated sample of planets, adding noise at the level we'd expect for the sample, and then trying to retrieve, again with hierarchical models, the constraints on the input parameters to the composition distribution model. And so with a sample of 50 planets, which is roughly the Kepler plus Keck radial velocity sample, I retrieved the composition distribution parameters, like the fraction of planets that are rocky, the power law parameters between planet core masses and envelope masses, and the degree of physical scatter in that relationship at a level of around 40% relative uncertainty. Whereas with 250 planets, which is about the scale that this project will characterize, we retrieved those parameters with 10% relative uncertainty. Now, these estimates are optimistic because real life won't behave according to the exact same model that I'm using to analyze the data, but I think this is still encouraging that with more planets, even with the current levels of uncertainties, we can bring the composition distribution of exoplanets and planets on the whole into greater focus. Okay, so that's our progress update, and I look forward to discussions throughout the meeting. Thanks.
Questions for Leslie?
Hi. These are very interesting results, especially the difference between the TDPs and the radial velocity measurements. So I was wondering, you're fitting these power laws to the data, which is of course a very good first step. And like, can you somehow assess whether like a power law is a good first assumption, or is there a way to improve upon that, or see if your data can tell you that there's more than a power law?
Yeah, so I mean, that's part of what Angie and I are currently working on right now. So me taking the direction of using planet interior structure models to, instead of taking power laws on planet mass and radius, trying to distill down to, okay, types of planet composition distributions might we expect as outcomes from planet formation? And can we actually distill like a core mass envelope mass relationship from the noisy mass radius measurements? So yes, that's work that's ongoing, and at least for the TTV sample, like the super puffy planets, the extreme low mass, low density planets do appear to be a separate population from the other planets, and that's what this plot was kind of trying to make that point, that if you just take a single component power law, that's not a good fit. You'd want some mixture model, at least, with two different components.
So one of the reasons I was asking was people have invoked sort of the 1.5 Earth radius, that they put the break in there, but I'm always wondering like, how much do you put it into the data as your initial assumption, and how much can you actually retrieve that from the data? So for example, could you infer that there is a break in this plot, say around like 5 radii or something? For example, if it's multiple power laws or different relations.
Okay, well, let me say that in my paper that wasn't actually part of this project, looking at where is the transition between rocky and non-rocky planets, there I was applying a mixture model. So there that allowed kind of some overlap in the rocky and non-rocky populations. And in the composition distribution model that I'm applying now, sorry, I didn't include the slide on it, I am, again, allowing some population of planets that are rocky and some separate population of planets that have volatile envelopes. So there, that would also naturally allow for some break with some grayness. I'm not sure if that addresses your question.
Yes, thank you.
Is the TTV method somehow more sensitive to the puffy planets? The RV, I can imagine, just treats the planet as a point source and perturbing the star, whereas the TTV actually depends on the mass structure of the planetary bodies.
So TTV models are also treating the planets as point masses. One aspect, so to get accurate transit times, it is good to have a deep transit that helps. And TTV measurements are, I would say, sensitive towards smaller mass planets on those longer period orbits. So that, another thing is, if you were to see a 8 to 10 Earth radius planet, perhaps you wouldn't prioritize that one for radial velocity follow-up because you'd figure, hey, that's a run-of-the-mill hot Jupiter or warm Jupiter, and not, yeah, a lot of the radial velocity surveys of a Kepler follow-up that are sensitive to planets that are smaller than, lower mass than 10 Earth masses, which is the sensitivity that you would need to measure the mass of one of those puffball planets, have been prioritizing planets that are smaller than 4 Earth radii. So that's another factor.
Oh, sorry. One more question.
What parameters do you have in the mass composition distribution?
Yeah, so for this initial trade study, I tried to make the lowest parameter model possible that still captured some of the main physical features that we would like to infer. So here I was simplifying things by considering a scenario where all the planets formed in situ. So setting water aside, or astrophysical ices aside for now, I considered a population of planets that are rocky with an Earth-like composition. And so for that population, essentially there was a mass and mass dispersion for their mass distribution. For the planet, the subpopulation of planets that managed to accrete and retain a hydrogen-helium envelope, there I took a power law relationship between the core mass and envelope mass. So that has 2 parameters, plus a parameter for the dispersion about that composition relationship, and again, 2 parameters to describe the core mass distribution. And then there was a final 8th parameter being the fraction of planets in the 2 populations. And I should say that power law relation between core mass and envelope mass, if you take the outcomes of some of the planet population synthesis models, like that Christophe Mordanzini has done, and if you squint, a power law relationship between core mass and envelope mass with some degree of intrinsic scatter is kind of roughly the simplest parameterization that you could come up with that captures the main features of those composition distributions produced.
Now let's make one.